Okay. So welcome everybody on our weekly seminar on theoretical computer science. Today we have Andrzej Grzesik, who is working in extremal combinatorics, extremal graph theory. Today the menu is something like Turán-type problems, which simply means that if a graph is dense enough, has sufficiently many edges, that you can find in that graph your favorite configuration. Exactly. And I am not going to tell you what kind of configuration will be today. The directed sides were okay, but it's not really the point as I read the abstract. So let's see what Andrzej is going to serve us today. The floor is yours.
Thank you very much. Yeah, Piotrek told me that I was speaking on this seminar something like 11 or 12 years ago last time, so it's high time to return with a completely different topics. So
hopefully not the same, huh?
Yeah. Oh, lots of things happen in the meantime. I even don't remember what I was talking about so many years ago.
I will look it up.
But definitely not Turán-type problems. Yeah, so as it was said, standard Turán problem is the following. So we forbid some graph and want to maximize number of edges in any n-vertex graph which does not contain this forbidden structure. Okay, so if I denote this Turán function, maximal number edges n-vertex graph not containing the graph here as a subgraph. And I want to emphasize that this is as a subgraph, not as an induced subgraph. Right? I'm forbidding not only this, but all supergraphs. And so this whole field started already in 2007. Mantel proved what's the extremal number of a triangle. And this is standard thing in every course in extremal graph theory at the beginning. So what it is, this is n squared over 4. And the graph that realized the maximum is a complete bipartite graph with equal paths. Yeah, so it's a balanced complete bipartite graph. And this is not called Mantel type problems, but Turán-type problems, because Turán generalizes inequalities to any cliques. So if I forbid clique of size k, then let me say roughly number of edges is 1 minus 1 over k minus 1, that's square over 2. I say roughly because, of course, this depends now on some divisibility conditions. I don't want to write ceilings and floors. But what's important is that the structure of extremal graph is very similar. So I have just few blobs, exactly k minus 1 blobs. And between the blobs, there are all possible edges and no edges inside blobs, and all blobs are of the same size. Yeah, the important part is that this was later generalized by Erdős, Stone, let me say Szymonowicz in the 60s. Let me check exactly. Yeah, 66. And what they prove is this how this function behaves in general. And in general, it behaves very similar. So it's 1 minus 1 over chromatic number of the forbidden graph minus 1. And square over 2 plus some lower order error term. Yeah, and this is basically solving the Turán problem for graphs. I'm saying basically because if the chromatic number is 2, then this parenthesis vanish equal to 0. So we have degenerated problem. We only know from here that the number of edges is subquadratic. And for such graphs, not much is known. Like even easy graphs, like even cycles or complete bipartite graphs, not everything is known exactly. But what I want to do on this talk is consider this problem for oriented graphs. So now we move to world of oriented graphs. And by oriented graphs, I mean a graph where I additionally put some orientation on edges. Yeah, so every edge has an orientation. And I want to emphasize that this is not the same as directed graphs, as you may know, because in a directed graph, you can have edges which are going there and back. And in oriented graph, I don't have such things. Yeah, so we can also think as directed graphs without loops and without edges going there and back. So orientation of a simple graph. Okay, and if I ask you such a Turán question for directed graphs, oriented graphs, so I can define in the same way maximum number of edges in an oriented graph without f as a subgraph. For example, if I take a directed cycle, what's the answer? Yeah, there is one graph which has lots of edges and has no directed cycle. It's just transitive tournament, right? I can put all the edges, all the vertices in a sequence and put all the edges directed one way. And of course, this is maximum possible number of edges. So the problem gets completely trivial in this case. What you can do, you can consider this Turán problem when the forbidden graph is acyclic. It doesn't contain any directed cycle. But then this problem becomes kind of generated as here, and it becomes really hard. Even if you forbid a transitive tournament, I think on 7 vertices, it's open. Yes, from 7 vertices, transitive tournament is already open. And if you want to think why it's happening so imagine I'm forbidding a transitive tournament on 7 vertices. And what could be a graph that has lots of edges and does not contain it? So intuitively, you will have some like groups of vertices, some blobs with some edges between, somehow oriented. Like intuitively, you will think about some tournament, yeah, between the groups. And what tournaments? As big tournament as I can without this transitive tournament. So basically, this problem is equivalently can be stated as a Ramsey problem. What's the biggest tournament that does not contain a specific size transitive tournament? And this problem was considered earlier many times, and in 60s there was a Moon and Erdős bound, and still this is the best bound that we have basically. And it's exponential, but we don't know even what's the order of the exponent. Yeah, so this problem is hard. Yeah, so you can imagine that if I consider this Turán problem for oriented graphs, it will be really hard. If it's hard for transitive tournaments, it will be hard for many others. There are some partial results. There are some also people in TCS department, Bartek Kierak-Jusnajeworska and the former student Sasha Novik. They had some nice results containing this, but this is not the thing that I want to discuss here. What I want to do here is look at these Turán problems from a bit different perspective. So instead of maximizing edges, I want to look at minimum degree. Minimum degree. Yeah, degree and edges are highly related. But what's happening if instead of maximizing number of edges, I would maximize minimum degree in a graph? Everything that I did here is the same. Yeah, because, for example, in case of triangles, minimum degree and half, which is here, is realizable without triangles. And if I go above, already my number of edges goes above, so I have a triangle. The same here, because the external graph is regular. And it happens also in this case, roughly, so with some lower order error term. Basically, you can say that if the minimum degree of your graph is at least 1 minus 1 over chromatic number times n plus lower order error term, then G contains that. Yeah, so Turán problem for degree instead of edges is not considered because it's basically the same. But for oriented graphs, the story becomes completely different, because now you cannot do the transitive tournament as maximizer. Yeah, because minimum degree is 0 here. Yeah, you want to have a graph, an oriented graph, which is kind of dense, but not dense in the sense of transitive tournament, but dense in the sense that from every vertex you can go out in many ways and you can come in many ways. Yeah, so the problem becomes completely different. Okay, so let's look how this problem, what's happening with this problem in such a setting. So I forbid some graph, some oriented graph, and I want to maximize the minimum degree.
Did you count out degree and degree?
Oh yes, that's a very good question. So you can look at maximum, minimum out degree. So minimum out degree is just minimum of out degrees of all the vertices. But you can also look at minimum in degree. It's symmetric, so basically the same problem, but also semi-degree. I will denote semi-degree by plus minus. And by semi-degree, I mean a smaller value between the out degree and in degree. So if you assume minimum semi-degree, then it's trash like bounding both out degree and in degree of every vertex. Okay, so let's start with out degree. I will then move to semi-degree. If I have a graph on just 2 edges, then this problem is trivial. You can check those 2 cases, either 2 edges going out or a path, and it's trivial. First non-trivial case would be a graph with 3 edges. There are 2, either transitive triangle or directed triangle. So let's start with a transitive triangle. Now, if I ask a question, how big minimum out degree you can have in an oriented graph so that the graph does not contain transitive triangle, then I can imagine that after a few minutes, most of you will come up with a reasonable construction. Just take 3 groups of vertices, each of size n^3, and connect all the edges in form of a directed triangle. This is very intuitive and reasonable guess. So now if you would like to prove it, then it would be that if out degree of my graph is above this, so it's at least n^3 plus 1/3, then G contains transitive triangle. Okay, and how to do it? The reasoning is quite easy. What you can do is start with any directed triangle. There needs to be at least one, because if not, then I don't have any triangles. And I'm in this case out degrees n4 at most. So with this assumption, I have at least one directed triangle. And now look at out degrees of those vertices. So if I look at all the vertices in the out neighborhood, those out neighborhoods cannot collapse. Like there cannot be vertex which is pointed from different, because it creates a transitive tournament. And so I have 3 groups of vertices, each of this size, together with those three vertices, which is above n, and the problem is solved. Yeah, I do the contradiction. So you see here, it was quite easy. Okay, so the next non-trivial case would be directed triangle. And for directed triangle, surprisingly, this is open. Yeah, so till this moment, everything was easy or trivial, and now we got stuck. So this is conjecture by Kacheta and Hackfist. From 1978. Yeah, and the conjecture is saying that if out degree is at least n/3, then G contains directed triangle. And now, why n/3? Yeah, finding a nice construction. This is not as obvious as there, but there are some ideas. So what you can do, you cannot have a direct triangle. So the next cycle would be a 4 cycle. Yeah, so, and in order to have dense graph, I want to somehow have those vertices grouped in cycles. So let me start with having 4 groups, each of size n/4, connected in a directed 4 cycle. Okay, it's good. I don't have directed triangle, but my out degree is far from the bound. It's just n/4. And what edges I can add? I cannot add any edges here, diagonal, because any edge is creating a direct cycles, but I can add edges inside. So what's the best I can do? I can just iterate it. Yeah, so I divide each into groups of 4 and iterate the construction. Yeah, I do it in the same. And then in each of those smaller blobs, I do the same. And I iterate until I run out of vertices. So what's my out degree now in such a graph? On the first layer, I have n/4. On the second layer, I have additional n/16. Yeah, then I have additional n/64, etc. And this is now easy to calculate that this is exactly n/3 in the limit. Okay, so since I'm stopping at some level, this is slightly below n/3. The conjecture is saying that if you reach n/3, then you have already a triangle. Okay, so this is the reason why n/3. But it occurred that you have more constructions. So for example, different construction would be the following. I take my vertices on a circle, and then every vertex I connect with everything in front up to n-1/3. Yeah, and similarly from this side, from 2n-1/3. Yeah, if I do it this way, then there is no directed triangle, because in order to find a direct triangle, I need to go around, but I have not long enough edges, right? The longest I can go is till here. If I repeat it 3 times, I'm ending up in 1 vertex earlier. Yeah, so there are no directed triangles, and my out degree is n-1/3. Yeah, so slightly below this threshold. What you can observe more is that you can combine those things. For example, inside the blob, I not necessarily need to iterate this construction. I can here put this construction, and I still have the same bound. I can put this construction on some lower level. Or I can do even more. I can find other constructions. For example, if I take 7 blobs and connect each blob with 2, like this, and just rotate it. Then there is no directed triangle. Yeah, it's a construction of this type. And if you iterate it, you have also n over 3. But you can mix those constructions. You can put this construction inside one of the blobs here, this construction there. You can mix them however you want. And this plurality of external constructions makes the problem hard, because if you now recall your lecture from graph theory or external graph theory and any of your favorite proof of Mantel theorem or Turán theorem, all those proofs are not only proving the theorem, but also giving structure of external graphs. Like if you use some kind of induction, like removing an edge and then using induction assumption, right? In order this proof to work, you need to have such inductive structure. And here, none of such proofs can work, right? Because you cannot remove some structure and use induction assumption, because there can be lots of different construction and the remaining can be in lots of different ways. Yeah, so that's the main reason why we cannot solve this problem. Despite people are really trying, in 2006 there was a workshop devoted just to this problem, hosted by the American Institute of Mathematics. Lots of people were trying to do any partial progress. There are some nice bounds proven or some related problems. And the nice thing is that after this workshop, they made a paper on arXiv, which is just summarizing everything that they managed to find out and prove on the conference, on the conjecture. But this is 2006. Since then, still papers are appearing related to the conjecture. Let me just mention what do we know about this. So, the theorem. Let's say that my out degree is at least C times N, then G contains the triangle. And I want to minimize C, right? Find the smallest one that the theorem holds. So already in 70s, Kacheta and Hequist, they prove C roughly 0.3819, so close enough. Later, Bondi in 70s proved 3797, then Shen in 92, 3542, Hamburger, Haxel and Kostoczka in 2007 proved 3531, Kratky, Kral, Norin already using flag algebra 3465, and recently Jean-Sébastien Sereni, Joannis de Verclos, and Jan Wolec, they decided to check everything, use high-speed computers, everything that we can do, plug in all together to huge program, and they managed to go to 339. So really, like, we cannot reach this 1/3 despite lots of tries. Yeah, but this is looking that's really, this should be the nice case. From recent results, let me mention one more. Rasborov did the following. He considered this problem, but he additionally forbid some structures. He forbid graph G to contain the following 3 graphs. So a 4-cycle with 1 edge rotated, transitive triangle without edge from the middle vertex, and transitive triangle without in edge to the middle vertex. He forbid those 3 graphs as induced subgraphs, and then he proved that the conjecture holds. Why it's interesting? Because those 3 graphs does not appear in any of the known external constructions. Yeah, so he's covering all the external constructions that we were thinking that there might be good. which is good and bad, because maybe there is a different construction which is blocking all possible approaches, and by forbidding those, he just get rid of this. Or maybe there is a different construction which is giving a bit better bound than 1/3. That's why nothing is working, and those constructions contain those. We don't know. Okay. This was about directed triangle. Semi-degree. If I change this conjecture with a stronger assumption, so now I want both out degree and in degree, at least, and third, then look that all the external constructions are the same. Yeah, they were having the same in degree and out degree. And it occurs that this is also open, and moreover, it's equivalent to older conjecture by Behzad, Chartrand, and Wall from 1970. And so additional assumption that your minimum degree is also satisfying this threshold is not helping. Still, we cannot prove it. Okay. What about other cycles?
And the constants from this mega program are the same.
That's a good question. I don't remember if they were assuming both in degree or out degree. I don't know. I would need to ask them. But I believe they tried, because it's natural to try with harder assumption. Yeah, so I think they tried with both in degree and out degree. Okay. Other cycles. For example, 4 cycle. If I ask you now, what could be the minimum out degree and in degree? Let's assume both, so semi-degree. In a graph, oriented graph, such that it does not contain C4. And now you can try in a similar way, so as dense as possible. But in this case, it seems easier because what you can do, you can take a blow up of a direct triangle. Yeah. It has already n/3. You cannot put anything more, okay, in any blocks. And it's a good guess. Yeah, so it would work for every cycle which is not divisible by 3. Yes? Yeah, if the cycle that we forbid is not divisible by 3, then this construction should have quite big semi-degree and should be good. That's a good guess. Okay.
Andrzej, so you're forcing all these structures subgraphs, but the result you mentioned by Rasborov, or was
Oh
it?
yeah, he was assuming that this does not appear as
induced, yes. That's what you said.
But they do not appear at all in the graph. Okay, maybe he was assuming as non-induced also.
Okay.
Yeah, because those structures do not appear here at all.
But that's
No, sorry, they appear. They appear here. Those appear here. So yes, I was right. He was assuming that those graphs do not appear as induced graphs.
And induced in a direct sense means that if you show me 2 vertices, there's no edge.
Mm-hmm.
Okay.
Yes. I have a conjecture. How to solve Kaczmar's conjecture, if you want. I think I made this conjecture. I think it was in 2017. So what you can do, if you assume that minimum out degree is at least, let me check, is strictly above 1/4 plus 1/4 squared, etc. up to some point. No, let me write it. Sorry, let me say it this way. Every oriented graph on n vertices without directed side triangle, but additionally assume and without transitive tournament, let's say on k vertices, 2k plus 1 vertices. Such graph has out degree bounded by this sequence. So intuitively, it's stopping this iterative construction at some level. Okay, if I stop after k levels, then I do not have transitive tournament of size 2k plus 1 to the power k plus 1, and this is my out degree. But why I'm advertising this? Because additionally, I want to say that each extremal graph, let me denote it by k, is a lexicographical product of C4 and the extremal graph for k minus 1. So what I was saying is that for k equals 1, I'm forbidding transitive triangle, then the best you can have is basically a blow up of C4 or any balance orientation of a complete bipartite graph. And then for k equals 2, I'm forbidding transitive tournament on 5 vertices. And what I'm saying is that the best you can do is a blow up of a C4 and inside each block external construction for forbidding transitive triangles. Yeah, and it continues. If I take k equals 3, so I'm forbidding transitive tournament on 9 vertices, I'm saying that the best you can do is blow up of a C4 and in each block external construction for 5. Yeah, so one can prove that from this conjecture, you can prove this conjecture, but this is nicer because of this iterative structure. Like you can control on which level you stop, right? You don't have this huge plurality of external construction. Okay, but this was just a question. Let me return to cycles.
Andrzej,
Yeah.
how are those other constructions for your for this modified problem? Do they give a worse bound?
Yes. So if you look at this construction, then it has a huge transitive tournament here.
Okay.
Yeah. So if you need to forbid it earlier, because I'm forbidding transitive tournaments, then it's destroying this construction with quite low bound. Yeah. So it's better to take a blow up of a C4. Okay, I should mention I prove it for k equals 1 and 2. So it definitely for 2 it shows that it really need to be a blow up of a C4 with external construction for a lower part. Yeah, so it may work for larger k and then it would prove it. Okay. If I'm forbidding cycle not divisible by 3, then intuitively blow up of a directed triangle should be fine. Yeah, while if I forbid some cycle which is divisible by 3 and not divisible by 4, so let's see, L is not divisible by 4, then one would expect that maybe just a blow up of a C4 should be fine. Right? Like intuitively. So such approach convinced Kuhn and Ostus exactly 2010 to state the following conjecture. So I take any length of the cycle, which is at least 4. So except the Kaplan-Heck's conjecture. I define K as the smallest integer greater than 2 that does not divide L. Yeah, so this is this intuition. Like if I have 4 cycle, then the smallest integer greater than 2 that does not divide L will be 3. If I'm in this case, then such smallest integer would be 4. Yes, and then for large enough, and every n-vertex oriented graph without degree, which is above this threshold n over k. Okay, so anything above contains my forbidden cycle. Yeah, so this is coming from this intuition that I should just look at the smallest blow up of a cycle I can consider, and this is giving me the threshold. Yeah, looks reasonable. Okay, and what they did is they prove it for k equals 3, which means that they prove it for all cycles of lengths not divisible by 3. Yeah, so if you choose any cycle not divisible by 3, then really blow up of a directed triangle is maximizing the minimum degree. Later, Ken Ostus and Diana Piquet in 2013, we prove it asymptotically for every k, and large enough. So let me say what it means asymptotically. Instead of this bound, they are assuming at least epsilon and more. And for every k, they say that if L is large enough, so L is at least some huge polynomial of k, then it will work, but only asymptotically. Okay, and what we did, and by we I mean together with Jan Wolec, and this will appear soon, we proved that the conjecture is wrong. So you can do better. What you can do, let's say you have a blow up of a cycle. Yeah, so this is, let's say this is the axiomal construction that they are assuming. So what I can do, I can add one vertex, connect it this way. Oh, not add, let me remove from here and put it here. So here I'm removing and put it here. Nothing changed yet. But I additionally put edges from here and to here. And now, because of this, I can remove one vertex here and I will not lose any out degree and in degree. Yep, I haven't lost. Sorry, both in degree and out degree. So the semi-degree bound is still the same. I just need to check if there is no cycle of length L. Yeah, but what's happening? Like before, without this vertex, all cycles that I was able to obtain were dividing, were congruent to 0 modulo k. Yeah, I could go only around. With this, I'm creating 2 additional reminders that I can use, because I can go around here or around here. Yeah, and everything else was already. So I'm adding 2 additional remainders. So I can now do, let's say, some A and some B. But if my L is of different remainder, then I'm happy. Yeah, I can add this, and it will enlarge my out degree. So I can repeat this process few times, exactly speaking, k minus 1 over 2 times, so that I'm adding additional vertices here and like keeping the out degree, in sense of a number, but reducing number of vertices. So this fraction will become bigger. And if I add not many remainders, then still I can control that cycle of length L will not appear. Is it intuitively fine? Okay. What's more, there are more things you can do. For example, in the case where k is 4, which means my cycle is divisible by 3, but not divisible by 4. So let's say that it's odd. So let's say that L is odd. Then what I can do from this construction, I can pick any C4, like fixed C4, and rotate those 4 edges. If I rotate those 4 edges, I'm not changing out degree and in degree at all. Yeah, so it's still an axial construction. So I can rotate how many I want, and this gives me completely different structure. That it's great. Yeah, which shows that you cannot prove it in a similar way. But there are even more things you can do. If L is 6, so I'm forbidding 6 cycle. It's divisible by 3, so I cannot use blow up of a directed triangle, but I can use blow up of a 4 cycle. But now let me divide one of the blobs into 2 parts and put arbitrary one-way oriented bipartite graph. This way, I will still not create 6 cycle. Okay, those edges are not enlarging my minimum in degree or out degree, because still vertices here will have small one. But it shows that there are more external constructions, so we need to take care of it. Okay. So now let me write maybe here. Oh, if it's camera here, let me here. What's the theorem that we can prove? So we can prove that. I will try to use this for any L. K be the smallest integer.
Andrzej, can we get back to the last example?
Yeah.
L equals 6 means that
I forbid 6 cycles.
Only 6 cycles, not like you can have cycles divisible by 6. You just forbid 6 cycles.
Yes.
Okay, sorry. I got it.
Okay, this was the conjecture. What we prove that if I put here k minus 1 over 2k, then this is on forcing L cycle. If L is not congruent to 3 modulo 12, And if L is congruent to 3 modulo 12, then even smaller bound is good. So n over k plus 1 over, in this case, it's divisible by 3 and not divisible by 4. So my k is 4. And it's, yeah. Yes. And moreover, this is the best possible. Yeah, so this is forcing L cycle, and you cannot reduce anything here. I'm going to the time. Okay, so how to prove such thing?
So it's slightly disappointing that the truth is uglier than
Then the conjecture.
than people believe in, yeah.
Yeah, but it's just a small change.
Well, it's 1/2 basically at the top, and
No,
here
no,
it's
no.
1/4, right?
Yeah, this is just basically plus half.
And they conjecture 1 over k, right?
Yeah, because
Which is-
whatever above and over k.
Mhm.
So it's just a small difference. But this makes harder to prove because you can have those small perturbations, right? So in order to prove it, what we did is we prove a lemma, which is giving us approximate structure. This way you can finish the problem. So what's the approximate structure? Because for L equals k equals 4, you can rotate those edges. So it's a bit different. Let me just show you a sketch just for the case when k is at least 5. Okay, so without this case where the structure is different. So in such a case, we prove that if the semi-degree of our graph is at least n over k, but with a small error term, 30k, the constant doesn't matter. So close to the conjectured bound, then G and G does not contain a closed walk of length L. So the difference between not containing a closed walk of length L and cycle of length L is that here you can repeat vertices and edges. Yeah, so this is a stronger assumption. But I have also a stronger thesis because we are claiming G is a subgraph of a blow-up. Okay. Yeah, so basically if you forbid not a cycle of length L, but a closed walk of length L, then you already need to be subgraph of a blow-up of a CK, as we claim. And even you don't need n over k, even a smaller bound is already forcing you to be there. I think I'm going slower with time. The question is if you want to see a sketch of this proof or sketch how to prove the theorem from this, or none, or both. People are afraid to ask. Yeah, so
Definitely one of them. Yeah.
What is more instructive for us? What would be more instructive?
like, proving this is, let's say, knowing how to prove such things is can be more useful because if you have a structure, then it's easier. But on the other hand, if you have you have lots of perturbation. Oh, okay, maybe I will do quick sketch of both.
Okay.
So if I want to prove from here the theorem, so what I can do, I start from here. I have a graph G which does not contain cycle of length L. And now I'm using just Semeredi regularity lemma to clean the graph. Yeah, I'm using Semeredi regularity lemma. I can obtain its subgraph by losing not much in the degree assumption. So I'm not losing too many out edges and in edges from every vertex, but I'm getting rid of all cycles of length, closed cycles of length L. Yeah, this is standard reasoning from Semeredi regularity lemma. This way, from this graph, by losing not much, I will obtain a graph with this minimum degree assumption and no closed walk of length L. Then I can use the lemma, so I know that structure of my graph is already nice. I have those blobs in this graph, but in the original graph, I could have a bit more. Yeah, I could have some small number of additional edges that were removed by regularity and some small number of trash vertices which were removed by regularity. Yeah, so now one needs to prove that number of those extra edges is big enough in order to find a cycle of length L. And we did it using additive combinatorics. One can prove using Kneser's theorem that each such edge is creating, each such extra edge or path through trash vertices is creating new remainder modulo k of cycles that I can obtain. Yeah, and using Kneser theorem, we prove that if the number of such extra edges is big enough, and big enough is given by the theorem, then we have enough many of them to create a cycle of length L. And that's the idea. Yes, and in order to prove the lemma, we do a different reasoning. So basically, we are in order to prove this, first step is to bound for any two vertices. I want to bound the length of the path from x to y. So I want to bound, it's like for every two vertices, there is some finite length path from x to y. And by finite length, in our case, it was something like 10 times k minus 1, 3 over 3. And how to do it? In order to do it, we basically were proving Kaczta-Heck's conjecture, almost. So what we do is we are saying that, like, look at the out neighborhood of the vertex x, and now if every vertex here has large out neighborhood, then from Kaczta-Heck's conjecture, I would find a cycle, and yes, and using this short cycle, I will find a closed walk of length L. So basically, some vertex need to have reasonably big out neighborhood outside. And we repeat this process in order to obtain like a tower of neighborhoods, which will contain at least n½ vertices. Yeah, building similar tower.
Can you repeat it again, please? I didn't get this.
So if every vertex has large out neighborhood inside,
every vertex on the path.
Inside this part.
And this part is what?
Out neighborhood of x.
Okay.
If every vertex has large out neighborhood inside, it will be too dense, and it will contain lots of short cycles.
By what?
By generalization of Kaczta-Heck's conjecture, but so generalization is that if you have out degree at least n over L, then there exists a cycle of length at most L. Yeah, so in case of triangles, it was n over 3 and 3. But you can generalize it. This is also open, but what we did is we proved it with some extra additional factor, multiplicative factor.
Okay, so you're bootstrapping from another theorem.
Yes.
And then this other theorem, don't you have the same place in the proof of the other theorem? No, here we are proving for L greater or equal 4.
No, and here I'm just, I'm proving some weaker bound, like let's say 30% weaker, stronger assumption.
Yes.
But this is enough so that vertices here cannot have too big out neighborhoods inside. So some of them need to have out neighbors outside.
Okay.
And then I repeat this process in this part. Still, they cannot have too big neighborhood inside. There is a vertex which needs to have something outside. And if you repeat this process long enough, then you will have those tower of neighborhood which are covering at least n half vertices.
This tower is built that there is a vertex that has a large neighborhood okay.
So I have n half vertices to which I can go in some finite number of steps.
Okay.
And this finite number of steps was 5 times this floor.
Okay.
And I do the same for in neighborhoods of y, yes. And since I obtain at least n half vertices in each, they need to collapse. This way I have a directed path from x to y, and they were chosen arbitrarily.
But you're proving that there is a path of short length between the two designated vertices.
And this is very nice. Why? Because if I have some structures that I do not like, for example, let's say a cycle with one edge reversed. Now I use this path from here to here. And what's happening, I have 2 cycles of short lengths. And if I have 2 short cycles of short lengths, I can build a closed walk of some length. This is a coin problem, right? You have coins of 2 values, let's say 2 and 5 zloty. And what values can you create using those 2 coins? Yeah, so this is saying me what closed walks of what length I can create. And since length of the cycle is reasonably big, because it's, for example, divisible by 3 and 4, so it's at least 12. And here I have bound that those paths are short. It can be proved that you can get rid of all such structures, I mean, cycle with one edge reversed, where the cycle is not long. And why forbidding such structures is fine, because now I can just start with any K cycle and look at the out neighborhoods, as in the first proof I was doing. They cannot collapse because it would create this forbidden structure. Yeah, so this is giving me the blob structure, and I can prove that this is really needs to be subgraph of the blow-up. There can't be anything like diagonal edges or edges inside, etc. Yeah. For k equals 4, you need to prove something different because this is not true, right? You are not the subgraph of blow-up. You can have different structure. But we prove that if your bound is close enough, then you need to be almost complete bipartite graph. Yeah, so you can rotate some of the edges, but this is still bipartite graph, balanced bipartite graph. And almost mean, but by removing some small sublinear fraction of vertices. And this is still good enough to use similar reasoning as here from additive combinatorics to find all the cycles.
So it's a good regularity over the.
Yeah. Like moving from here to such a lemma needs regularity. Yeah, for L equals 6, it's a different reasoning because the length of the cycle is too short to use any kind of coin problem or anything like this. Basically, closed walk of length 6, it's almost the same as cycle of length 6. You cannot repeat too many vertices in a 6 cycle. And in this case, we are doing more exact computation. I mean, we are trying to force the structure exactly without any regularity. Yeah, so, and also there is this bipartite part that one need to remember, but this is still doable. Like it's similar ideas as here, but with more colorful counting. And this way you can prove the theorem completely. I was planning to do something more, but already 1 hour passed. So maybe I will leave it for a future talk. So I will finish with the advertisement.
I won't be alive.
No. So there are lots of results recently in extremal graph theory, where one is not maximizing number of edges, but maximizing number of other subgraphs. In case of cycles, you can consider forbid one cycle length and maximize some other cycle length. There are lots of results of that kind. In particular, Jagiellonian and Shapira, they prove what's the order of magnitude, because it's not obvious what could be the order.
Order of magnitude of what?
So you are forbidding some cycle length, let's say C6, and you want to maximize number of cycles of some other length, let's say C3.
Okay.
Yeah, and it's not n cubed, because then you would have a 6 cycle. It's some lower order, but what order? Yeah, so Jagiellonian and Shapira, they proved exactly what's the order of magnitude.
For all these combinations?
Excuse me?
For all these combinations?
Yes, for any.
Okay.
Yes, and there are also lots of particular results when you forbid specific cycle length and maximize specific cycle length. And the Erdős pentagon conjecture was exactly of this type. So you forbid triangles and want to maximize pentagons. This was open for like 26 years before slug algebras. Now it's known, but we have only this computer assisted proof. But still, there are lots of other problems of this type. And in case of directed cycles in oriented graphs, you can also consider such a problem. And it occurred that one can prove order of magnitude, and this was done by Justyna Jaworska, Bartek Kielak, me, and Tomek Ślusarczyk last year. And also together with Piotr Kuc, we solved this problem for some particular cycle lengths, and it occurred that the structure of extremal example is completely different. So it's not the case that it's a blow up of a cycle with some small additional extra edges, but it could be different types of structures. It can be a blow up of a cycle with blobs which are transitive tournaments. It can be blobs with iterative structure. It can be blobs with bipartite graphs, one-way oriented, or just blow-ups of cycles. So there are lots of different.
But extremal examples for in the case when you forbid some
cycle and maximize other cycles.
Okay.
And depending on length of those cycles, forbidden and maximized, the extremal examples are very different. So it's not so easy that you have always like one parameter as here k, but really lots of strange things can happen there. And it depends on various number theoretical properties of those two cycle lengths. So advertisement of next lecture may be of one of my co-authors, because my time is over for the next 10 years. Thank you very much.